So, very good afternoon to you all, and welcome to the fourth session on the series Geoprocessing using Python. So, today, in the last lecture, we discussed about two fundamental libraries named NumPy and Matplotlib. So, today we will discuss about raster data processing. So, yesterday actually we just briefly read a small JPEG image using Matplotlib, but when you want to read geospatial data, say a geotiff image which has coordinate information and projection information associated with the image as well, so that the image can be projected on the map. So for that, actually, Matplotlib's read function, image read function, is not so powerful, right? So then, for that function, uh, for this we will discuss today. We will use a different and more very powerful library called GDAL. So before going to the GDAL, I will just briefly touch upon what raster data is, how raster data is represented. Anyway, in the first lecture, this has been covered in detail. Just for the sake of completion, I will just touch briefly upon the fundamentals of raster data. Then we will go to the processing using Python. Right. So if you so raster data represents objects variables on the Earth's surface, or like any object variable, or objects or variables on the surface of Earth or near the surface of Earth. If we are representing them, those features, as a matrix or a grid of cells, right? So that what we call raster data. So whenever we are representing any feature on the surface or near the surface of Earth using a grid of cells, right? So all these small cells, what we call those cells, we call pixels, right? So raster is an image with matrix of values, and the values in those cells might be representing some information. That may be some observed attribute about the feature which we are looking. Like it might be a reflectance, surface reflectance in particular wavelength, or it might be temperature or the rainfall at that particular cell, or say the geographical area which the particular cell is representing on the surface of Earth. Right. So then a band of a raster, like a raster can have multiple bands. So bands of a raster correspond to different variables. Right. So all the bands in a raster, like our raster images, can have multiple bands. So every band might correspond, it corresponds to different variable. But usually, but it has the same structure. Right. So so like this you can see, this is a raster image containing multiple bands. Here every cell might represent, say it might be a temperature or a rainfall at some particular base time, say T0. And the second layer might be representing the same area, but the temperature at, say, different time, T1, T2, T3, and so on. Right. So this way, a raster image can have single band where we are just representing a single snapshot in the time, right? Or the raster can have multiple bands. Now multiple bands can contain different information, like it can be a single, it can be a snapshot of that geographical area on a time t0 only, but those the information might be reflectance in, say, different electromagnetic bands, or it might, or the band may be representing a temporal information, like first band represent temperature at t0, time t0, then second band might be representing at temperature at time t1, and so on. Right. So this is so like if you this is how an image is represented. So an image is represented as a matrix or grid of cells. So if you zoom into the small area on this image, so the image looks like this cell of a grid of small cells. So every cell representing some information, like here you can see the intensity, or it is showing some color. So then ultimately in the computer's memory, the entire image is represented as a matrix of numbers, right? So numpy will be helpful in processing the images. Right, as we have discussed that some, like raster bands, so some rasters have single band of data, while others might have multi-bands data, right? So the basically a band is represented by a single matrix of cell values, and raster with multiple bands contain multiple spatially coincidence matrices. So what I mean, like if a raster image contains more than one band, so all the bands will have they will spatially coincidence. Like it means that all the bands are representing same geographical area on the surface of Earth. Right. So whether it is a multi-band image, say in the red, green, blue band, or if it is representing some temporal information, so all the bands will be representing like the same spatial area, like they will be representing same spatial area on the Earth. Right, so some examples of simple single band rasters are maybe digital elevation model, where we represent the elevation of surface, or it can be a temperature at some particular time, say particular time t0, or panchromatic images are examples of single band rasters. Then single band rasters can be represented maybe either using a binary image, where the cell value can be either 0 or 1, or it can be a grayscale image, where the intensity levels or grayscale level are different, or we represent the image using different shades of gray, like different varying shades of gray. Suppose if you are representing an image using 8-bit data, so in that case we can have 256 different grayscale levels, or an image can be represented, if it is a classified image, can be represented as using a color map as well, like all ones they may be representing some class, so that can be represented by, say, yellow color. Then all twos might be representing class 2, so that can be represented using a different color. So like this, so either you can represent single band images can be binary image, grayscale image, or we can even represent them using some even continuous color map or discrete color map, or maybe continuous color map also you can represent. Then multi-band raster, a satellite image, for example, commonly has more than one band representing different wavelengths from the UV through visible to infrared portion of the electromagnetic spectrum. Right. So an image can have more than one band. So if you represent like red, green, and blue bands separately, so they can be like the different. We can represent all bands separately as a grayscale image. When we combine three primary colors, say red, green, and blue, then we make, by combining three primary colors, we make a colored composite, right? So that what we call a color composite. Or so when so like this, when we combine three bands together, then we get a colored image. So these are some examples of different color composites. So now we'll come to the library. Like this was the introduction to raster data. Now let us see how do we read raster data, basically using a powerful library called GDAL. So GDAL stands for Geospatial Data Abstraction Library. So basically it is a translator library for raster and different vector geospatial data formats. So basically you can say that GDAL is a library that is basically used for reading and writing different geospatial data, maybe whether it is a raster data or vector data. So actually, as we said, that GDAL can read multiple raster formats. If you know about raster data is available in. So actually, there are numerous formats, file formats in which raster data is available. Say GeoTIFF, JPEG 2000, or PNG, JPEG. So these are also kinds of raster data representation, or IMG format, or NV. NV also gives some proprietary formats. ADAS image in IMG format. So like this. So what happens? So these all formats differ from one another in multiple ways, right? So some formats might compress the data before storing it. Some formats might not be compressing the data. Their block sizes will be different, and and some, how do they interleave the data? Some may be interleaving data at the pixel level. Some formats interleave the data at band level. So GDAL, so as we said that GDAL can read a variety of formats. So what GDAL does for a user? So GDAL presents a single raster abstract data model. So irrespective of the underlying format, like whether it is a JPEG image, JPEG 2000 image, GeoTIFF image, or big GeoTIFF image, whatever be the image, whether it is using compression or not. So the all images will be represented by an abstract model, right? So that abstract model will just capture the, or it will provide the essential interface to the user, and all the underlying details, like how the data is internally stored, will be hidden from the user. So it will give a high level interface to all to the users, irrespective of whatever format. Like independent of the data format, it will give a high level interface. Like suppose if your user wants to query how many bands are there in the image, what is the width and height of the image, which kinds of what data type is used for representing the pixel intensity, or what is the projection information, transformation. All this information can be fetched by JIDAL uniformly across the formats. Right? It's like there is no, like if you see, for reading Word document we have Microsoft Word, for reading PDF document we have uh, Acrobat Reader. But in case of JIDAL, either whether it is a GeoTIFF image or IMG image or NV image or whatever kind of image, JIDAL is a single software which can read all these formats. Plus, like JIDAL also comes with a variety of useful command line utilities also for data translation and processing. Someone not comfortable using Python scripting, then command line interfaces are also available with JIDAL, so that with that you can automate many of your tasks. So if I read about the advantages of JIDAL, so JIDAL, one of the most uh, useful feature of JIDAL is that it is free and open source. You need not pay anything for using it. Then it supports over 80 plus image formats and different map projections. So it has command line as well as C, C++, Python, and Java R APIs also are available. So depending on your choice, you can choose these things. Plus, it is used extensively by the world's large geospatial data services. A lot of geospatial data services are using JIDAL extensively. Plus, it has an extensive test suite and active developer community as well, which are continuously contributing to development of JIDAL. Plus, JIDAL has an exclusive support for vector data sets as well. So as we said that JIDAL, irrespective of the format, irrespective of the underlying format, so raster data is represented by an abstract data model called JIDAL dataset. So whatever may be the format, so ultimately to the user it will be represented as an abstract dataset called JIDAL dataset. Right. So a dataset now once we represented an image using a data set, then it has some attributes and different functions for operating on that raster data set. Like it has some attributes like for calculating the size of the image. Then suppose if you want to fetch some particular band, there are multiple functions available for fetching those bands and manipulating those bands. And manipulation actually you need to do in NumPy or some other things. So dataset also is responsible for for the georeferencing transform and coordinate system definition of all bands. A dataset itself can also have associated metadata, and a list that as a list of name value tuples. Like so, our abstract data model, what we are calling JIDAL dataset, will contain all information which we require to operate on that particular image, like querying the data set, then fetching individual bands, calculating or getting the projection and transformation information so that the image can be projected on the map and so on. So like this is, if you see it graphically, the JIDAL's raster data model looks like this. So irrespective of the format, all the images, raster data, all the images will be represented by an object called data set. Right. So the data set in turn will have multiple bands. Depending on the number of bands available in your image, there will be multiple band objects inside the data set. Like in the data set object, there will be different functions available with which you can fetch these bands individually. Then it has the geo transformation and projection information associated with the image as well, stored in the JIDAL dataset, right? So then in the band in turn will contain for ultimately data array, as we discussed that ultimately an image is a matrix of numbers, right? So the data array will be representing the matrix. Then it can have some associated overview bands as well, right? So these are what we call reduced resolution data sets, right? So these are the images which are covering the same spatial extent, but they have bigger pixel size, or the resolution of the images is, you can say, that is coarser. So these are advantageous, like when you have very high resolution image, and suppose if you are looking at a very large area, right? So if the image is drawn or rendered at the native resolution, so it will be very time consuming, right? So when we are looking at the larger area, then the coarser image will be drawn there. So as you zoom in and zoom in, so then you get the native resolution image, right? So the band over so over these overview bands helps in drawing the image at different zoom levels, basically you can say. Right, so then let's talk about map projection. So map projection is a way of representing three-dimensional surface of Earth in a two-dimensional surface, right? So geotransformation is a mathematical transformation for converting a three-dimensional surface to a two-dimensional map so that it can be represented on the map. So whenever we are doing a transformation or converting a three-dimensional surface to two-dimensional surface, there definitely will be some distortions, right? So then depending on our application, we preserve some of the shape. Maybe either some transform some projections will preserve shape, some projection will preserve area, and some will preserve directions or angle, right? So but we have to compromise on one of these. So these projections are the transformation of 3D surfaces to two dimensional surfaces, so that can be rendered on a computer screen or a plain paper. Right, then there are then when you represent it on a map, then map on a two-dimensional surface, then we need a coordinate system so that we can identify individual pixel or refer individual pixel by maybe that coordinate. We can identify that pixel on that grid. Right, there are numerous conventions used globally for representing coordinate system for the map data. Right, so the dataset coordinate systems are represented in there are different formats for that. One of them is OGS WKT, well-known text string. So in that the transformation information or transformation, this coordinate system is represented in WKT format and PROJ4, and there are many more things. So when we talk about an image coordinate system, so in the in image coordinate system, every pixel is identified by its pixel number and line number. Right. So the columns we call pixel number, and the rows we call line number. So for identifying, as we discussed yesterday, like whenever we want to identify an individual pixel on a two-dimensional plane, so or a plane, you can say that. Then for identifying a individual pixel, we need to refer by its pixel number and line number. So that is what we call coordinate image coordinate system. Now these same thing can be like, you can convert them to the real world coordinate. Like what suppose if you these also we will with the help of affine transformation information attached to the image, we will convert from the image coordinate system to the real world coordinate system. Like suppose if you want to know the like pixel number 5 at pixel number 3, like if you say that this particular pixel, like at pixel number 3 and line number 5, which geographical area or which geographical area, what are this latitude and longitude on the surface of Earth. Suppose if you want to know, those things can be calculated with the help of geotransformation information attached to the image, right? So with the help of geotransformation attached to the image, we can convert that from the image coordinate system to its real world coordinate systems, right? So now let us see how do we read an image. So for this demonstration, I have already downloaded some images, right? So I have used the list 3 images of the Haridwar area. So that image I will be using for demonstration. Like so for installing Jidal, so the easiest way for installing Jidal on your system is you must install is using Conda, right? So actually, as we discussed in the first lecture, so Conda is quite easy to install. Like just download from the internet and you can activate it here. Then for installing Jidal on your Conda environment, there is only single command, like you can install Conda install Jidal, right? So that install Jidal to your system. Otherwise, like if you are not using Conda, then sometimes it's very cumbersome to install Jidal to your local system, right? So it is advised that you better use Conda for installing Jidal. So but here we are already using Google Colab. So Google Colab already comes with pre-installed Jidal. So in case of Google Colab, we need not install anything on our Google Colab. So right, so the name of package, as we once you if you install JDAL to our system, so the name of package is called OSGeo. Right, so now inside OSGeo there is a package called JDAL. So from OSGeo import JDAL is the way for importing JDAL module from the OSGeo. OSGeo the name is the name of package, and JDAL is the module inside that entire package, right? So how do you import JDAL from OSGeo? Import JDAL. Then these are other associated libraries. For one is NumPy is for manipulating that data, and Matplotlib as usual we have been using for display. And this HTML and other things I will come back to the later. Right, so first thing what I am doing here, I am just changing my working directory to the directory where my data is available. Right, so actually I have already mounted my drive here. So if your drive is not mounted, you can just click on this icon. So this icon mounts your drive. So actually when you want to upload files to the Google Colab, so there are two ways. So one thing is, like, suppose if you want to store your data permanently, so then what is then the way is you just install your data to your Google Drive and mount that Google Drive to your Google Colab. Otherwise you can upload your data here as well, directly on the Google Colab as well. But the disadvantage of this is that once you restart or log out of your session, this data will get lost. Right? So suppose if you want to do permanently, then you just store your data on your Google Drive and then mount that drive here, like I have done here. So like right. So then your entire Google Drive will be visible here as a drive folder. Then inside that you can just see here. So my all of my data I have stored in this particular directory. So I am just switching over, changing my directory to this working directory, so that whenever I want to refer to a file, I need not give its full name, because like these all functions whatever we are using, they because they look for the file name in the present working directory, right? So that I need not give the entire path name of my files. So because of that reason, I'm just changing the working directory to the directory where my data is available, right? So in this folder I have a geotiff image called name haridwar.tiff, right? So now let's inspect or get some information about that image. Right, so the basic function in JDAL available. The basic function in JDAL, suppose if you want to quickly get basic information about your image, so there is a function called JDAL.info. So if you call JDAL.info and pass it the name of file and the format in which you want the output, right? So that suppose if I want the output to be represented in JSON format, where the data is represented in key value pairs, so then I will pass the format is equal to JSON, and if I just print the information, so then you can see that a lot of information about the image gets printed here in very nicely formatted way. And so it says that band. So this particular image has like band 1. So if this image has multiple bands, so band 1, this is the block size of band 1, this is the color interpretation. So these are the max and min values of the band, and other associated information like this bands, max, min, metadata. Then this is the projection information. Projection information about the image. Then like these are the coordinates of the image. Like these are the extents of image in geographic coordinate system, right? So like this you can by JDAL.info you can get the basic information about the image. Now suppose similar information, suppose you do not want to use JDAL.info and you want to just read the image using Python and just using the Python JDAL utility, suppose if you want to calculate it yourself, right? So the basic thing, suppose if you so first thing, for opening an image using JDAL, the basic function is open. Right, so for opening an image, you need to call JDAL.open actually. So first thing that you need to take care of, this is Python being case sensitive. So the O in the open is capital O. So if you just try to type JDAL.small open, so then it will give you an error. Right. So for opening or reading an image, we need to call JDAL.open and pass it one mandatory argument, that is the name of the file. Right. So if I call this, so then here you can see that it has returned us an object called osgeo.jdal.dataset, right? As we discussed in the JDAL raster data model. So irrespective of the format, the image will be represented as an object called dataset. Right, now in this dataset there will be there are multiple attributes and functions available to get more information about the image, right? Like GDAL info was returning us some list associated with the file. So similar way, suppose if you want to fetch that here also, you can call ds.get file list. Then if you wish to query the width and height of our image, then we can call raster x size. So it says that 2000 pixels are there in the x direction, and raster y size gets us the height of the image 2000 pixels in the y direction. And suppose if you wish to get fetch the projection information associated with the image, right? So then we can call gs.get projection. So with the help of this projection information, the image can be projected on the map, right? So this is the projection information of our image. So it says that the image is in projected coordinate system, which is based on the WGS84 geographic coordinate system. So it is UTM 44 north. Like the image is represented in UTM in projection UTM 44 north, which is based on the GeoGCS WGS84. Right? These are the other parameter of the well, so similarly, suppose if you want to calculate the geo transformation information or affine transformation information, right? So with the help of these 6 parameters, we can calculate real world coordinates of any pixel in our image, right? So GDAL.get geo transform, if you see, so it gives us 6 elements, right? So first element represents the longitude of 0 pixels, like this is in projected coordinate system, so this is in meters. So this 0th element represents the coordinates of 0 pixel. Then the second is the resolution in x direction, like this is a 5-meter resolution. And third is the rotation of the image in x direction. And if the image is not at all rotated, means north is directly up in our image, it means it is 0. Then this is resolution or latitude of the 0 pixel, and this is the rotation in y direction, and this is the resolution in y direction. So like suppose if you want to calculate these things, then these are things. And suppose if you want to calculate, now suppose if you know the pixel number and line number, right? So suppose if you want to calculate which area on the surface of earth this particular pixel represents, or maybe center of that pixel, right? So suppose then we want to go like what are the latitudes and longitudes of that pixel, right? So for that in GDAL there is a built-in function called GDAL.apply geotransform. So if you call this function apply geotransform and pass it the 6 element transformation information and your pixel number and line number, so then it calculates the coordinate corresponding to that pixel number and line number. Right, now if I see that, like these are the coordinates of our upper left corner, right left upper right corner, lower left and lower right corner, like these are the coordinates of 4 corners of our image, right? So then similar way you can calculate the center as well. Then like if there is some metadata associated with the image, that you can fetch using a function called ds.get metadata. So then suppose if you want to calculate how many bands are in your image, then you can call ds.get raster count. It fetches you like there are 3 bands in our image. Right, now suppose if you want to iterate over all of these bands in our image one by one and calculate some basic statistics, or like are there any overview band associated with that image and all, like some basic information about that image if you want to calculate. So here what we are doing, we are just iterating over all of these bands one by one, right? So then we are like our data set, suppose if you want to fetch an individual band from the raster data set, you can call the function get raster band and pass it the band number which you want to fetch. So that will return you a band object. So the band object then has again multiple functions attached to it, like you can calculate are there any overviews attached to that. Like you can say that with all these bandits, there are 3 overviews attached. Like original size of our image was 2000 by 2000 pixels, but overview 0 is just at the half of the resolution. Like this is now the same area is represented by 1K by 1K pixel, and the third level it is 5K by 500 by 500 and 250 by 250. Like in every overview level, the pixel size is getting doubled, or you can say the number of pixels are getting reduced. And so similarly, suppose if you want to calculate the basic statistics on the each of the bands separately, like you want to calculate, like suppose if your image has 3 or 4 bands, and suppose if you want to calculate minimum, maximum, mean and standard deviation across each of these bands together. Now the same thing, like we can iterate over the all bands one by one, and just there is a function called band.compute statistics. So then if you pass it, the approx OK is equal to false, it fetches back the mean, min, max, mean and standard deviation across the that particular band. Right now, this we have tried to calculate some basic statistics and the transformation and projection information about that image and all. Now, ultimately, as we said that ultimately an image is represented using a matrix of cells, right? Now, suppose if we want to see that how that array looks like, right? So, as we are actually now the process is quite simple. So, first thing what we need to do, you need to remember till now just one thing. So I will just open it once again, like ds is equal to jidal dot open and pass it the name of file. So first step is jidal dot open, pass it the name of file, right? Now suppose if you want to fetch an individual band, like all the other properties actually we have already queried before. Now suppose if you want to fetch an individual band, like suppose if you are interested in extracting some information from the band 1. So then for that you need to call now the function on this data set get raster band and pass it the index number of your band. So as we discussed yesterday, the indexes in NumPy array were starting with 0. But in case of GDAL, the band indices start with the number 1. So suppose if you want to fetch band 1, you need to pass the argument as 1 only. Right, so band ds.get raster band if I do, so it will fetch us a band object. Now in that band object, there will be multiple attributes. Like suppose if you want to just fetch the data from that band. Right, so in the band, there is a function called read as array. So if I call read as array, so if I just, it will be done as a now two-dimensional NumPy array. Right, now you can see that these are the two-dimensional NumPy array. Like these are the intensities of all the pixels which are there in our image as we discussed. Like this is how the image is represented in computer's memory. Like now from these numbers we cannot make a sense. Now suppose if you want to visualize the image. So as we discussed yesterday, for visualizing a two-dimensional array, the function is called plt.imshow. And to this function we need to pass our two-dimensional NumPy array. If we just do this, you can say that the image is represented like this. So actually the contrast of image is not so good, because of that the image is not looking good. So we need to just do some enhancement to make it better. But anyway, we'll do it in the subsequent sessions. Now suppose if you want to fetch all the bands together, now we need to iterate over all the bands one by one and just show them. And so this way we can display individual bands in our image. Like here you can see now all the two bands actually we have fetched back. Like this, only one band was already there. So now like this, you can visualize all bands together also in your image. So this was all about visualizing a grayscale single band or grayscale image, right? Now similar way, suppose if you want to, now let's see how do we visualize a multi-band raster when our image has more than one bands. So there are many, as we can say that a satellite image generally captures can have many bands. Like some satellite images can have 5 bands, some satellite images can 6 bands, 7 bands, and so on. But ultimately, whenever we represent the image on the computer's screen, so then what we need? We need just only 3 bands only, like 3 primary colors, right? Red, green, and blue. So out of these 7 bands, any band we can represent as red color, right? So there we have multiple options available here. So suppose if you want to represent, so there are multiple options. Like band 1, we might route to, like band 1 you can represent using red color, band 2 we can represent using green color, and band 3 you can represent using blue color. So when we combine all these 3 primary colors, red, green, and blue, then we get a composite color. Now if our satellite image has more than 3 bands, then we have multiple choices. Like out of these 7 bands, we can select any 3 bands to be represented as red, green, or blue color, right? So these things, when we, so like these combinations of what we call are these we call false color composites, right? So when we create a color composite by choosing a different wavelengths to be with different wavelengths in red, green, and blue color, that what we call false color composite. And one of that standard is called standard false color composite, when we represent NIR band as red color, red band as green color and green band as blue color. That what we call a standard false color computer. So that like this, as anyway now we have multiple choices. So then we can create multiple false color composites using if there are many bands on your image. So the image which we will create false color composite is a list 3 image. So the list 3 image has bands green, red and NIR. So sphere band actually I have not taken. So like we will see that how do we create a false color composite using these three band combinations, green, red and NIR. And so we will be changing like NIR band. Sometimes NIR we will be representing as red and red as green and green as blue, and we can choose anything like NIR we can represent as green color as well. Green can be red or red can be blue and so on. So this way we can create different colors composites. Now let us see how do we create a standard false color composite using our GDAL. Right. So first thing I will be opening the same file once again. So anyway the file is open, but just for completion I will open it here. Right. Now suppose if you want to read all bands for your image together. So previously what did? We just read the entire image, then fetched the individual band from that image, then we represent it in an array. Now suppose if you want to don't fetch individual bands separately from your image and you just want to fetch all bands together, right? So for that our data set also has an function called read as array. Like if you call ds.read as array and pass it the list of bands which all you want to read, right? So then it returns you a three-dimensional array. Like here we are just reading band 3, band 2 and band 1. Now if I see the shape of this multi underscore data, so it is a 3 cross 2k cross 2k. So this is what we call it. This is in the format CHW. So first channel, then the height, then width. Right. So by calling ds.read as array and pass it the list of bands which you want to read, you can read the entire contents together as well. Now suppose if we want to create like suppose you want to we are just inspecting the data. Now suppose if you want to display the image, like we want to create a band color composite from that, then first thing what we need to do, we need to convert it from the CHW format to HWC format, right? So where the channel comes like, because actually matplotlib's im show function accepts data only whether the data should be single two-dimensional array or it should be in the format HWC, right? So actually whenever we read the data using GDAL, it returned us data in CHW format. So by calling this np.transpose, we are just reorienting the axes, like we are converting this CHW format to HWC format. Right. Now if I see the shape of multi underscore data now after execution of this step, you can see that now it is 2k cross 2k cross 3. Earlier 3 was at the top. Now for visualization, the same function like plt.im show. Then you can say that the image is represented. But one thing, when you display an image using plt.im show, you need to take care of one thing, that so whatever band you are passing to im show, so the first band will be represented always in red color, second band will be represented as green and third band will be represented as blue. So this so suppose if you want to create a different color composite, that care you need to take while reading the data from your image. So whenever you pass the data to im show, so first band will always be represented represented in red color, second band is green and third in blue always. Right. Suppose if I want to create a different color composite, right? So suppose I want to represent band 2 in red color, band 3 in green and band 1 is blue. So that care I need to take while reading the data from using GDAL only, right? So here I have changed that sequence. Now if I just, then I am converting it to HWC format, and if I plot the, now you can see that the same image, if you change the band combination, looks very different, right? So this is one combination. Like this, you can create any false color composite quite easily using data. Like here in this combination, first band 1 we are representing as red, band 2 as green, and band 3 as blue. Now if I see, the image looks quite different. Like, so actually different features are identifiable clearly in different band combinations. So for that purpose, the scientists or the application user use different false color composites for studying the feature in more clearly, for so that they can study the feature which they are looking at more clearly. So then there are multiple ways, like suppose if you want to read a partial data set, like suppose your data set is very large and you just want to read a portion of that image, right? So then you can call the read as array, you can pass multiple arguments, like instead of reading from 0 pixel, just read from the 600 and 600 pixels, and just read 512 by 512 pixels only, like just read a subset of your image. Right? So that also can be done quite easily. Like here, we have just read the subset of our image. So now this was our GOT format. Now suppose if you want to read read HDF data, right? So sometimes you will be getting the data in HDF format. So hierarchical data format is a data file format designed by National Center of Supercomputing Applications, or NCSA, to assist users in the storage and manipulation of scientific data across diverse operating systems and machines. HDF file consists of a directory and a collection of data objects, right? In the directory there will be multiple data objects. So every data object has a directory entry, again directory entry containing a pointer to the data object location and information defining that particular data type. So you can say that this is self-explanatory data. So presently there are basically two popular formats. One is HDF4 and HDF5, right? So both of that you can try. So now we will try. So you can see that HDF data is arranged in the set of groups. So every group will be containing a data set, that what we call scientific data set, and then as these are represented inside HDF format, right? So when you try to read HDF image or hierarchical data format using GDAL, so there will be multiple sub data sets. So once you a data set now will contain sub data set, and sub data set in turn will contain bands. So when we were using a flat file format, so there the data set was directly containing the band. But when you try to read, HDF image is in the raster data model is represented like a data. Ultimately, it is represented as data set only. But data set in turn now will have sub data sets. Then there will be bands. So for this particular demonstration, I will be using images from ISRO's satellite named INSAT 3DR. So INSAT 3DR is a dedicated meteorological spacecraft designed for enhanced meteorological observations and monitoring of land and ocean surfaces for weather forecasting, disaster monitoring, disaster warning, right? So INSAT 3DR is configured on I2K bus with, there are basically two payloads in INSAT 3DR, two instruments, you can say that. One is imager and another is sounder. So both of them has different applications. So we will be focusing basically on the images provided by the imager payload. So INSAT 3DR imager provides imaging capability of the Earth's disk from a geostationary altitude. Actually, the INSAT 3DR is not a polar remote sensing, or you can say the polar orbiting satellite. It is a geostationary spacecraft. So it has like cameras inside in visible range, so 0.57 to 0.72 micrometers range, and 5 infrared channels, SWIR, MIR, water vapor, and TIR1 and TIR2 bands. Right. So the ground resolution at the sub-satellite point is nominally 1 kilometer by 1 kilometer for the visible and SWIR bands, and 4 by 4 kilometer by 4 kilometer and MIR and TIR bands. And for WB band, it is at 8 kilometer by 8 kilometer. So then there are different, like if you go to the MOSDAQ portal of ISRO, so you can search on the Google like SAC MOSDAQ. So it will give you the link. So from the MOSDAQ portal, you can download these INSAT 3DR images if you are interested in doing meteorological observation, or suppose if you want to experiment with imager or sounder data, so what data whichever I will be demonstrating here, you can just go to the MOSDAQ portal and download it freely from there. Right, so we will not concentrate on other bands. We will just today's demonstration will just visualize a visual band, like visual band which is in 0.5 to 0.72 micrometers. So as I said that, because inside 3DR is a geostationary spacecraft, so it is continuously monitoring same geographical area on the surface of Earth. Like, so if you see a remote sensing spacecraft, they will be monitoring the same area maybe just once or twice in a day, right? But this geostationary spacecraft are continuously monitoring, like they are monitoring the same area on the surface of Earth continuously. Like, if you see the insert 3DR images, you will get every half an hour a new image. Like, if you are developing some applications where you need continuous monitoring, right? So there you can use these images. So the images are available in, so actually I have already stored the image in this particular folder inside my drive. So inside this I have the images like 3DR, and these these are of some images, like the images 915, 515, 915, 445, and also these are images there. Then we will just randomly pick up one of that image and see how do we read that image using GDAL. There are other libraries also which we can use for reading these HDF5 files, because this is H5 file, or you can say this is HDF H5PY, X-ray. Other libraries also you can use for using this, because our lecture was all about GDAL, so I will be using GDAL only for reading this image. So first thing, I am changing my working directory to the directory where the data is available. Then I am just creating a variable file name in which I am storing the name of file which I want to read. Right, file name. Then the other steps remain same, only gdal.open. Open file names, and we are just passing the name of file which we are going to read. Now, as we said that this is a HDF, hierarchical data format, right? So here main data set directly will not contain bands. Now here the data set will contain sub data sets, right? So for fetching sub data sets, now we will be called the function called get sub data sets. Now get sub data sets will fetch us different sub data sets inside that. Right, now if I see the SDS, it will be looking something like this. So these sub data sets will have two things in there. One will be the name of the sub data set or group, whatever we were calling, and its description. Like here you can say, now if I iterate over this entire sub data set using this, that will becomes it more readable. So here you can see that the SDS is this IMG and if I print the description of each sub data set, like what this sub data set, which information this sub data set is representing, you can say that first it image in MIR band, image is SWIR, image in TIR to visual band with water vapor and azimuth elevation. These are some information about the image, and these are the sub data sets, SDS. Now suppose if because as we said that for the demonstration we will be using this, we will be reading the visual band. Sorry, it was SDS underscore name. So these are the names of our sub data set. Now suppose if I want to extract or read the image corresponding to the visual band, right? So to the GDAL, now I need to pass the name of this file. Like as we discussed that there is a core data set and core subdirectories. Inside that different sub data sets are there. Right? So now if I want to read this particular image from my main HDF file, so then I need to pass the name of this file as to my gdal.open file. Like gdal.open, then I will be passing this HDF5 and the name of file. Right, now this is a data set. Now in this data set I can fetch individual band, and if I just call read as array, now this is, I have got the entire data. Now suppose let us see how does it look like if I call the function. So this is the image looks like. There you can see clouds. Now as I said that because the geostationary satellites will be monitoring the surface of our same area continuously 24 hours, right? And InSat 3DR provides the surfaces images of the Earth every half an hour. Like suppose if you want to develop an application where you want to track the movement of clouds, right? So like now let us see how do we create a simple animation using these InSat 3DR images. Right, so now for the demonstration, I have taken some 3 or 4 images, images of every half an hour. Now let us see how do we create a nice animation using these images using Matplotlib. Right. So for that, for creating animation, actually we need a very software or library called FFmpeg. So this is very good for creating animations from different frames. Right. So first you need to install this. Suppose if you want to install it on the Google Colab, you can just install with web app opt-get and install FFmpeg. And so this is very small software, so it gets installed quite fast. Now in my same directory, I have stored some files, right? So now if I just run, I'm just this base directory .glob. With that, I'm just searching which all files are there with this particular name. Now if I search the names of these files, so if I just print the files, so in my directory, I have available these files. Right. First file is at 7:15, 7:45, 8:15, 9:15. So one file might be missed. 9:45, 10:15. Like I have these images of the Earth at these almost half an hour time interval. Right. Now suppose if I want to create a animation by combining these all frames together. So for that, first thing what I need to do, I need to read all these images one by one and store them in a say 3-dimensional array or a list. Right. So here what I am doing here, I am iterating over all these files one by one and opening each of these files one by one, then reading the data from that file and appending them to a list. Right. So then finally I'm converting that list again to a again to an array. So now if I see the frames, so frames will be a 3-dimensional array. So like this is a 3-dimensional array. If I see the shape of frames, so shape of a frame is 6 cross 116 cross 1317. Like every 2-dimensional array is representing an image as at time t0, t1, t2, and t3 and tn. Right. So now for creating an animation out of these frames, like creating a video by concatenating these frames together. So Matplotlib has a package called animation. So if we import that matplotlib.animation as animation, right, then so first thing is we need to create a base figure, right? So for that, suppose we will first put a frame 0, 0th frame in that base animation. So figure dot first, same thing we are creating first a figure and subplots, then we are calling imShow that creates a base frame, then setting that, then we need to implement a function called update. Actually the animation will be continuously calling these function update continuously. So we need to define a function called update to which we pass an integer index, so that index will be fetching this. With the help of this index, we are just fetching individual frame from our combined frame. Like our frames data set is storing all our frames concatenated together. Like so in the update function, we are just picking one by one the frames from our entire sequence of frames. Right. So what happens, this animation keeps on continuously calling this update function. Right. So the update function must be passing to the animation next frames in a sequence. Right. So this is how do we create an animation. So once I call this, so this animation will be calling this update function one by one. So in the update function, we need to implement or update function must fetch our frames one by one from our entire sequence. Right now, suppose if you want to convert this to HTML5 video, now animation object has already been created. Now if I call animation to HTML5 video, you can see that the animation gets created here like this. Then you can convert it to an mp4 image or jpeg image or the image of your choice, right? Like this, you can say that the animation is created. Right, so like this quite easily, suppose if you have a sequence of frames, you can create an animation like this. So maybe for entire day as well, like the where you can see the movement of clouds. So with this, I come to the end of session. I will just briefly touch upon what we have discussed. So we basically discussed about reading raster images using GDAL. As we discussed that raster is a translator library for reading and writing vector as well as raster data. So today we focus just on reading raster data. Then we so as we discussed that irrespective of the underlying format, right? So the raster data is represented in GDAL using something called a data set object. Right, so the data set object will contain, in turn, will contain all details about the image like bands, transformation information, and projection information, and so on. Then we tried to read a simple GeoTIFF image using GDAL, and the simple function for reading an image is gdal.open, and just pass it the name of file which you want to read. Right, so then from the images you can fetch the bands and so on. Then we discuss about a format called HDF, where when once you read an image, you don't get you get in get a data set, but that data set directly will not contain bands. It will contain sub data sets. So now first you need to open those sub data sets, and from that sub data sets you can extract individual bands, and then from band you can extract data. So then we discussed about insert 3DR imager. Right, so insert 3DR imager, as we discussed, that it provides the images of Earth at every half an hour. Right, so so we just fetched some 3 or 4 6 images for half an hour interval, and then we tried to create animation using matplotlib from that images for maybe tracking movement of clouds. Right, so thank you very much for attending the session. If you have any questions, you can post them on the chat box. We will try to answer with the best of my knowledge. So thank you very much.